So hello again, welcome back to all of you. So for this second half of the morning session, we are lucky to have Annalisa talking us about cosmological hydrodynamical simulations. Please, Annalisa, when you want.
Yes, thank you very much. Can everyone hear me well enough? Give me a yes with the voice.
Yes.
Perfect. Thank you so much. Also notice that not every time I see the chat. All right. Thank you very much.
I will take care of the chat. Don't worry.
So today we are going to talk about cosmological hydrodynamical simulation, but actually for galaxy formation and evolution. So I have in mind really a practical guide in practice to cosmological galaxy simulation. So this is how we should call them in short. Because indeed the idea today is not only the one of describing the evolution of dark matter, as you have done in the previous class, but of dark matter, gas, stars, supermassive black holes, possibly photons. And so as we were waiting for starting and as I'm introducing the lecture, you're seeing here a scanning through a modern state-of-the-art simulation. We call it TNG50. From top to bottom, you see a space of 30 megaparsec. And this is a snapshot at the current time at redshift 0. And we're scanning through the various matter components, as indicated on the top right, that can actually now be sampled and modeled in modern cosmological galaxy simulations. In fact, so now we are going, for example, the colors here represent the magnetic field strength. And soon something a bit complicated is the oxygen 7 column density. But this is what you're seeing here is essentially an obvious cosmic web, a large scale structure. But these simulations are important for us because what we really care about is also to simulate galaxies on very small scales. So for example, these are galaxies from that same simulations, many of them as we could map them in stellar light. Okay, so my name is Annalisa Pillepich, so the reason for which I'm telling you all these things is because I work on this topic. Now, I have started as doing bachelor and master in physics at the University of Pisa, at the time in theoretical physics, and then I moved for a PhD in theoretical cosmology. At that time, I really started doing pencil and paper calculation with second order cosmological perturbation theory applied to the so-called 21 centimeter cosmology. But then I went for 2 postdocs, first at the University of California in Santa Cruz and then at Harvard. And here I moved more and more towards numerical cosmology and more specifically numerical galaxy formation. I then landed in 2016 in Germany at the Max Planck Institute for Astronomy, where I'm a group leader in numerical and theoretical astrophysics. So indeed, so what is the research I'm thinking about with my team? So we develop, execute, analyze, and compare to observations numerical models to understand galaxies and the mergers of structures in the universe. So our favorite models are the ones we are going to talk about today, are cosmological large volume simulations that include gravity, magnetohydrodynamics, and galaxy processes like star formation in order to model together population of galaxies. We run them on thousands of computing cores at national supercomputing facilities, and a simulation project that I've been working on and that will come up during the lecture is the so-called illustrious TNG, the next generation illustrious. I'm actually also working on more generally galaxy clusters as astrophysical laboratories and cosmological tools. Okay, so during the next 1 hour and a half or so, I will give you really some keywords and pointers to understand both the foundations and the limitations of this kind of numerical models. Since I expect most of you are actually physicists, I will give you a very brief, very quick context on cosmology and galaxies, and what are the goals of cosmological galaxy simulations, the basic ingredients and the landscapes of state-of-the-art cosmological galaxy simulations, and then more into details about the gas fluids, the theoretical foundations of galaxy formations, the numerical solution of the Euler equations, element of smooth particle hydrodynamics, Euler hydrodynamics, some mentioning of moving mesh codes, and some available cosmological codes. I hope I will be able to convey what numerical resolution means in this kind of simulations. And at this point, I think we will do a break. So when it's 1:15, please let me know, or 1:15, 1:20 now, let me know. And at that point, we will actually then focus on how we model the physics of galaxies, so star formation, stellar evolution, feedback from stars, and supermassive black holes. I will give you examples of state-of-the-art simulations and some selected results that you guys who are thinking about our matter, gamma rays, etc., should have in mind. Okay, so let's get started with the cosmological context. And if there are questions and I don't see them in the chat, please speak up. So we now have a very good understanding of the initial conditions of the universe. The initial condition of the universe, say 380,000 years after the Big Bang, are actually essentially the initial conditions of our numerical models. And we know that at the time, the universe was essentially homogeneous and isotropic, but for small density, or here depicted temperature, fluctuations of the orders of something like 10 to the minus 5. 13.8 billion years of cosmic evolution go by, and this is what we would see in the sky if we were to look at it in the 2 micron wavelength, where you can see now the matter density distribution on large scales as sampled by galaxies. And now the density contrast is of order of many factors, or up to thousands, depending on the scales on which you're looking at. Another way to look at these distributions of galaxies in the sky is by actually plotting them as a function of redshift or distance in billion light years or megaparsec. Here, again, this is the results of a galaxy survey, which was called 2DF. One point here is one galaxy, not one star, one galaxy made in terms of millions and billions of stars. And you can see here that on this scales, you can start to see the cosmic web, the large scale structure of filament and possibly sheets, if you were to look at it in 3D, halos and voids that I think you have touched upon in the previous classes. Now, if the universe on very large scales above 100 megaparsec could be considered and described as homogeneous and isotropic, this is certainly not the case below scales of 100 megaparsec or 10 megaparsec or so. And so, for example, you can easily see that the distribution of galaxies are not uniform, all right, on these smaller scales. If we go to even smaller scales, so say, for example, the scales of 60 megaparsec or so, and we see around us what stellar light we get, we can immediately see that our neighborhood is very complex. We are part of a galaxy with a neighboring Andromeda galaxy. We are sitting in a so-called local group. Next to us, there is the Virgo cluster, and then there is Coma cluster, and farther away, more massive and larger structures. Now, then if we look at even on smaller scales, so on the scales of galaxies, clearly the universe is not homogeneous. And I'm going through this panorama because I want you to have very clear in mind what kind of spatial scales we're talking about. Galaxies are on spatial scales of, say, from 1 to, say, 100 kiloparsec. And we know from observations, from telescope observation, either from the ground or from space, that observed galaxies come in many shapes and forms. So these are actual stems from the Hubble Space Telescope in a particular wavelength, in an infrared wavelength. And these are not post-processed image stems. As you can see, that some of them are disky, some of them are much more smudgy or kind of with no features. Also, observed galaxies range across masses and spatial sizes. So what we call galaxy go from, say, 10 to the 4, 10 to the 5, 10 to the 6 solar masses in stellar mass, up to 10 to the 12 solar masses in stars. They also span something like a couple of orders of magnitude in sizes. The Milky Way is a galaxy with something like 10 to the 10.5 solar masses in stars, and its disk has a typical disk length of 2.5 kiloparsec, to give you an idea. So we also know that galaxies can live in very different environments. Some of them are in isolation, like the one on the left, and they're unperturbed and easy by themselves. Others are in groups of a few, like the Milky Way. But others are actually orbiting around more massive galaxies, together with other hundreds or even thousands in the galaxies, clusters of galaxies. All right. And some of them are actually merging. These are actual images from actual observations of interacting and merging galaxies, where different wavelengths are here combined in different colors to give you a bit more flavor of what could be happening. All right. And so also galaxies are not just made of stars. So in these galaxies, for example, the stellar light is actually associated to the emissions from cold gas, like hydrogen. So for example, on the left here is the same galaxy. If we see it in optical light, which gives you the distribution of the stars, in UV light, that gives you the distribution of. Yeah. I have a question here. In these pictures, are the dots also other galaxies? And I don't know anymore in which picture. So, Isabel, can you speak up at which point you were asking?
Yeah, so I think these pictures of the galaxies. Or
yeah. So some of them are extended, and you can easily see that there are galaxies. These are satellites of Andromeda. Others, so these, when you see the diffraction spikes, these are really point sources, and these are stars. But other points can easily be forward or background galaxies. Yes, thanks.
Okay,
thank you.
Thanks.
And yeah, so galaxies are not just made of stars, but also gas. So we were saying here, for example, same galaxies in optical wavelength, in UV light. The UV light shows you new young stars, but also on 21 centimeter wavelength at radio level. And this is telling you about neutral hydrogen. This is the same galaxy. These are different galaxies also seen at radio wavelength, but you can see the diversity of morphologies even in the H1 gas in this case. Also, gas permeates the cosmos, and it's in between stars and also around galaxies. So for example, galaxies as stellar bodies are surrounded by gas. And so for example, here you see a galaxy, the stellar disk is this one. You guys hopefully can see my mouse, and if you don't see it, please let me know. And you can see here in these colors, like, oopsie, I went too far. In these colors here, in the red, this is actually depicting cold molecular gas that is moving perpendicular away from the galactic disk. So in astronomy, cold gas is gas up to 10,000 degrees, okay? And hot gas is millions of degrees. And so for example, if we zoom out and we look at galaxy clusters, so now this image on the left is something like, I don't know, of the order of tens of kiloparsec maximum. On the right here, we're talking about hundreds of kiloparsec, if not a megaparsec. Here, the violet light color gives you X-ray emission, which is telling you about very hot gas. All right, and finally, to finish this overview, now we know that most massive galaxies even host a supermassive black hole at the center. So our own Milky Way has a supermassive black hole at the center. The luminous source is called Sagittarius A, and you might have heard about these amazing results that are now depicted here, for which now the community can actually measure the motions of individual stars around this elusive black hole. And the motions has been now so detailed that they can confirm the general relativity is a good descriptor of gravity, and also the mass of the supermassive black holes of Milky Way is very well known. It's actually quite small. It's 4×10⁶ solar masses. So it's more than 1,000 times smaller than, for example, the supermassive black holes that sits at the center of the galaxy, that sits at the center of our neighboring Virgo galaxy cluster. And its supermassive black hole is the one that made the news like last year or so. It's the first imaged supermassive black hole. In fact, now we know that the more massive a galaxy is, the more massive its central supermassive black hole. So why am I telling you all this about galaxies? You guys are mostly probably physicists. You care about cosmology and gamma ray. Well, first of all, because galaxies are the smallest cosmological structures. But second of all, galaxies are where things happen, are where mostly cosmic rays are accelerated, gamma rays are produced. And as you could hear in previous classes, it's where active galactic nuclei or active supermassive black holes are showing off these amazing actions. Like these are hundreds of kiloparsec, and these plumes of material is seen in the radio. And at the center is a galaxy, and at the center is this supermassive black hole that we think is driving this energy manifestation. This is the other one I showed you earlier. This is an example, we think, of gas thrown around a galaxy because of supernova explosions. And I don't know whether you've talked about it already, but if we look from our position in the Milky Way, in the galaxy, towards the galactic center, this is what we see, the figure on the right. In red is gamma rays. Yes, extending above, these cocoons are the Fermi bubbles extending something like 9 kpc above and below the disk of our galaxy. And in cyan are X-ray, is X-ray emission, recently seen by the eROSITA telescope, extending like 14 kiloparsec. So these are all signatures of movements of gas in and around galaxies, driven by energetic phenomena that happens within the inner regions of galaxies, rather whether supermassive black holes or stellar supernova explosions and things like that. And so we want to model galaxies. So we cannot do dark matter physics and gamma ray physics if we do not understand galaxies. This is my pitch here. And so now let me go to the goals of cosmological galaxy simulation. So essentially understanding the functioning of galaxies in the cosmological context means to be able to model them. And we're talking about numerically model them. So the goals of the frontier in cosmological galaxy simulations is really to formulate self-consistent models for the formation and evolution of galaxies. But these models have to function across the mass scales and spatial scales I showed you before, across 14 billion years of cosmic evolution and across environments. They have to be realistic. So meaning they have to return observed statistical properties of galaxy populations, but also physical properties of galaxies at the subgalactic scales, as the one we are observing these days in the sky. And in turn, if you are an astronomer, you want to use these models to quantify, say, what galaxy properties tell us about their formation, or to provide interpretation to astronomical observations. But more in general, and as we aim in my team as well, ultimately we want to infer via comparison to observations what galaxies can tell us about the underlying assumptions of gravity, matter, and the functioning of the universe as a whole, and therefore what can tell us about dark matter, dark energy, and assumptions on the description of gravity. So again, so at the forefront of the research in this modeling of cosmological galaxy simulations, we have a series of desiderata. We are at the point where we are really pushing the frontier, and we want, first of all, to include the relevant physics. We want to account for the cosmological context. We want to simulate large ensembles of galaxies. This simulation have to be realistic in a way, at some level, and we want to reach crucial physical scales. So just I give you an example. What I mean by accounting for the cosmological code a moment ago, yes, the galaxies are not isolated. They merge with others. They belong to galaxy clusters. So these structures come from the evolution of the large scale structure. And so then, which in turn is determined by the evolution of the universe as a whole. So therefore, we have to account for the cosmological context. Now, as you can see, this is a challenging problem. As I tried to convey you earlier, the scales that are encompassed by this problem are huge. We go from the large scale structure of the universe two individual dark matter halos at the center of which galaxies can be observed and should be modeled, all the way to supermassive black holes and star formation happening at the center of galaxies. And we are going through more than 10 orders of magnitude in spatial scales, and orders and orders of magnitude in time. In time. Yes. All right. Also, galaxy formation is not just a multi-scale problem, but it's also a multi-physics problem. So I think it's a good way to understand what I'm saying here by now dividing a bit the regimes. So the community has become very good at modeling how we go from the initial conditions of the universe to 14 billion years after, by modeling the large-scale structure of dark matter, or say galaxies, on large scales. But now this is where we stand. We want to also simulate the smaller scales, from large scales to the scales of galaxies and below. The first step has been relatively easy now since 20 years, 10 years, I think, because large scales are dominated just by gravity. And on very large scales, the universe is homogeneous, isotropic, or the deviations are not from linearity are not too large. But then as you go to smaller scales, the universe becomes more and more structured, and gravity is not the only force of relevance. So the gravitational collapse is not the only things that matter. And also there's, as I mentioned already, there's many phenomena that happen at the center of galaxies that have back reaction. They propagate back from small scales to large scales, making this a very coupled problem to solve. Now, when we think about the gravity, I just want to give you an idea that I'm sure it came out this morning earlier, but I think this is the way to understand the formation of structures, that gravitational instability drives the formation of structures, right? Gravity is only attractive. And so even if at the initial conditions, like the ones suggested by the cosmic microwave background, there's just tiny deviations from homogeneity, these can only develop further, making higher density regions more and more dense, and lower density region less and less dense. And so then, based on this very general idea, we can also now understand the results of numerical simulations that only simulated gravity-dominated regimes. So these are things that you probably saw this morning. We are now just flying through a large-scale structure of the Millennium simulation, and here the color gives you the density of cold dark matter. And you can see halos within filaments, sheets, and voids, and subhalos within halos, the cosmic web. All right. But now in this lecture, we want to simulate the small-scale regimes. So we want to go from dark matter or darkness to the light. And as I tried to convey earlier, just with the images, well, galaxies are complex. They're made of stars or cosmic gas, which we call baryons. We come back to that in a moment. And they are characterized by a series of things we know because we observe them and actually encapsulate very complex physical processes. So we know stars form out of so-called molecular clouds or more general sites of star formation. They can form in clusters. They can form globular clusters. They can die in supernova explosions. Dust, gas, and dust. Dust is complex molecules in astronomical jargon. Are all within the galaxies, and we know this phenomena of feedback from supermassive black holes and stars. There's a question from Lorenzo. I said in the previous lecture, which are the size limits for the confidence of the simulation of a galaxy? Lorenzo asked about this in an hour. Then it will be clearer, yes? Okay. This is all the point of my more technical parts of the lecture. Okay. At the core of our modeling of galaxies in the cosmological context is this picture. So our standard cosmological model predicts the formation of dark matter halos. So for example, cold dark matter halos. Cosmic gas permeates the cosmic web as well as dark matter halos. But galaxies, we know, form at the center of these gravitationally bound structures. Galaxies are made of stars. Stars form out of gas. And this is possible because gas can actually reach higher densities than what dark matter could, because the gas can cool, can radiatively cool, can concentrate at the center of the potential well, fighting the pressure forces that would actually want them not to collapse. And they can reach densities that we think are needed to form stars. So this is the very basic idea that we could tell to our grandma. But in fact, this is not an isolated concept, because again, we want to do all this in a cosmological context. And so we apply this very general idea to forming galaxies at the center of halos across orders of magnitudes, across the cosmic web, across environment, whether they are forming, emerging more and more massive halos, or are remain in isolation in so-called voids, and whether they belong to filaments and sheets. Okay? All right. So we come now to describing the basic ingredients of these galaxy formation models and the landscape today. Our starting assumptions are those from our favorite cosmological model. The majority of the state-of-the-art numerical galaxy formation simulations are all assuming the standard cosmological model, the lambda cold dark matter that you have seen in the previous days. So lambda cold dark matter tells us that there is a dominant matter component, okay, dark matter. But then if we were only to evolve dark matter, we would only do a gravity-only simulation. But in fact, the idea of large-scale cosmological galaxy simulation is to co-evolve dark matter, gas, stars, supermassive black holes, possibly magnetic fields, possibly photons. So these are the matter components. Then you have to decide what physical processes you care about or you can afford to model. Gravity, for example, dark matter interacts gravitationally. So gas not only interacts gravitationally, but also via hydrodynamics. So you must, solve for fluidodynamics coupled to gravity if you want to have a consistent picture of the coevolution of dark matter and gas. In fact, then there are also atomic processes you may care, photon propagations and other things. When you do a simulation, then what you want to decide is what kind of domain you are simulating. And when we think about large-scale cosmological simulation, we are thinking about cubes, literally 3D cubes of representative portions of the universe with periodic boundary conditions, which we evolved from the initial conditions at some point at very high redshift down to redshift 0, or earlier, if you want to stop earlier. But the initial conditions are indeed distributions of dark matter components and gas, in case, which are almost homogeneous and isotropic. And then, boom, you switch on the solution to your physical processes and equations, okay? And the initial conditions, the way the matter is distributed, almost homogeneously and isotropically, but for very small fluctuations, are statistically consistent with the statistical properties of the matter distribution, for example, as given by the cosmic microwave background, all right? Now, based on these descriptions, now you could also orient yourself around what are the cosmological galaxy simulations. Yeah, what about the MHD processes? We'll come to that in a moment. So MHD is simulated now in some, but not all, of these galaxy formation simulations. And it's a question mark whether magnetic fields are important or not for galaxy evolution itself. Certainly they are for star formation. And we'll come back to it in a moment. Yeah. Now, see, so this morning you saw dark matter only simulations. And now we are talking about dark matter plus gas, plus stars, plus supermassive black holes, possibly magnetic fields and MHD. I'm talking about projects like they're called Illustris, the next generation Illustris, Eagle, Horizon AGN. These are all simulations that came out in 2014, 2015 or so, not earlier. So about 10 years after the very cool simulation like Millennium in the past. These are on large scales, And you may have heard also of other projects, which on the left, again, dark matter only, on the right, galaxy formation simulations. And these are so-called zoom simulations. They're still cosmological, so galaxies are allowed to merge with others, but the resolution, and which we'll come to it in a second, is all focused on one individual object. These are projects like FIRE, Apostle, Eric, Auriga. I was wondering, can you please raise your hand if you have heard at least a couple of these names in your career so far? Okay, a few, but not many. So my lecture will be useful. Very good. Thank you very much for participating. All right, good. Now, so let's go a bit more into the detail. This was really like a very general introduction. And let's talk about the baryonic fluid. So guys, bear with us. The jargon is a bit funky, right? So components of the usual material objects, ion, atoms, molecules, even electrons, we call them baryonic matter. And you may think, okay, but what the heck? Electrons are not baryons, all right? Yes, but it's fine. But on large scales, very large scales, the universe is electrically neutral, all right? And so the mass density of the, and because the mass density of the electron is negligible compared to the one of the ions, say, like proton and neutron, then like people have started to just simplify the nomenclature and call everything baryons. Okay, so now baryons in the universe clearly do not only interact via gravity. This is why we need to solve for hydrodynamics. And I just want to give you an idea of what we mean by this. These are images, astronomical observations, and all these colors depict some state of the gas. And you can see these motions, and you can imagine that these motions are not only driven by gravity, but also by fluid dynamics. So for example, these colors here are, this depicts the bullet cluster. And in this bullet cluster, these are two gigantic galaxy clusters, they are merging, and the stars and their matter are in a certain position, but the gas sloshes and goes in different positions in the merger compared to the collisionless material. This is the center of the Perseus cluster. These are two galaxies merging, is the antenna galaxy. You might have seen supernova images, the star formation sites. This is molecular gas, or even these are called jellyfish galaxies. And again, the color here shows you gas. And these tails of gas is as a purely hydrodynamical phenomenon, run pressure stripping. Okay, and so, and gas dynamics is certainly more complicated, no, than collisionless system. And so, for example, in the universe, and because we're dealing with gas, we can have shocks or fluid instabilities. So I think everybody knows shocks, but let me just go through them. For example, hydrodynamical flows can develop shock waves when you have a jump of density, velocity, temperature, specific energy by finite amount. And you can connect the states of the gas pre-shock, after shock, you can define a Mach number, etc. But also very important for astrophysical applications are fluid instabilities. Like the Rayleigh-Taylor instability is the one that you get if you put two fluids of different densities, one density, the one with high density at the top of another, and the gravity field goes down, and the fluid naturally develops instability, or the Kelvin-Helmholtz instability, when you have two fluids having different velocities moving in a parallel manner, and they also have different density or different velocities, and as you can, and you produce these Kelvin-Helmholtz instabilities with the formation of these eddies, etc. Now, baryons in the universe, there's a good news. They can be modeled as ideal gas. And so, as we said earlier, gravity is the dominant regulator of structure formation on the largest scales, but on smaller scales, the hydrodynamics of the gas becomes important. But in cosmological settings, gas flows are such that the densities are usually low and the friction is usually negligible. And so we can actually describe gas with Euler equations. So these are the Euler equations. They are a simplified version of the Navier-Stokes. Strictly speaking, the Euler equation is the one on the second row. But you can close the system of equation with a mass conservation equation, energy conservation, and assuming a state of the gas like an ideal gas. Here, the variables tells you the fundamental physical properties you need to know to evolve your gas, which are mass, velocity, and energy. You can also derive pressure, all right? And so, for example, yes, you have the Euler equation that is it connects the momentum with pressure, etc. All right. So this is the foundations of the description of gas dynamics. And now I want to give you a bit more inputs about the fundamentals or foundations of the idea of galaxy formation. So we talked about gravity. You have seen this morning and yesterday how large-scale structure form. We have talked briefly about the baryonic fluid and now a bit more about galaxy formation. Okay, these are the key ideas of modern galaxy formation that rely on the cosmological setting. I mentioned it earlier and now I'm going into more details. Okay, structural formation is driven by gravitational instability. Stars form out of gas, actually out of very dense gas. Their matter halos form out of gravitational instability, but they also get a spin due to the tidal torques of the cosmic web on larger scales. Galaxies, this is the standard model for galaxy formation, form inside their matter halos via a two-stage collapse, okay? So first, you have the collapse of the dark matter component, but then you also have the gas follows for a while the gravitational collapse of dark matter. And it first undergoes shock heating, but then it can also cool because gas can lose energy via radiative processes. We will see them in a second, and therefore can reach density, fight against the pressure, and reach higher density in the center of halos. We think that the formation of these galaxies can be understood because of the cooling of gas to the dark matter halo centers via conservation of the angular momentum of the dark matter halos upon collapsing. And the elliptical galaxies form in the very, very, very simple scenario, simply via merger of these galaxies. All right. This is the picture that came up in the 70s purely from theoretical and analytical thinking. And the key point of all this picture is the cooling. This is something that may sound a bit funky, but let me see if I can convey the idea. So I go again into more details with respect to the previous slides. So the gas initially is the same spatial distribution as the dark matter. The dark matter halo collapse. The gas is heated by shocks as it falls into the gravitational potential well of the dark matter halo, producing a hot gas halo that is in principle supported against further collapse by the pressure of the gas itself. In fact, in this phase, the gas attains a so-called virial temperature of the halo. If you're interested, it's on the right-hand side, but maybe I can skip this detail. But the point is that gas can also cool from the hot halo through radiative processes. So this is the role of cooling of this, and this is what we mean by dissipation. So gas can radiate. And this is what we call a sign of dissipated processes. These are all processes for which internal energy is transformed into another form. And so gas can lose energy by a number of radiative processes. And as the gas cools, the pressure of the gas drops and the removal and there's no any more pressure support that fights against the gravitational collapse of the gas, which can then sink at the center of the dark matter halos and form possibly stars. So let me give you an idea of what these radiative processes are. There are many mechanisms for gas cooling, okay? So for example, if you have a plasma, you have your electrons scattering off the nuclei, and you produce Bremsstrahlung radiation. So this happens for very, very hot gas. Or you can have, say, collisional excitation, meaning collisions between atoms and electrons. These essentially produce jumps of energy levels, but at the point where you transition between energy levels, you can produce photons, and again, you radiate away photons or energy. You can also have inverse Compton scattering of semi photons by electron, etc. So the only important thing here is that many of these processes are effectively collision now, and they depend on collision among species, electrons or atoms or molecules. And essentially, the importance and efficiency of these various cooling processes depend on density. For the collisional ones, it goes like density to the square, the temperature of the gas, and the chemical composition of the gas, whether you have neutral atoms, for example, or complex molecules. And so we typically describe all this in terms of the cooling function, which is this quantity here depicted here. And the cooling function tells you essentially the possibility for a certain amount of gas to cool, yes, depending on the temperature the gas is found at, the density, and the composition. So for example, if you look at the blue curve, this is a bath of hydrogen and helium only. And if the gas was very, very hot, we would only have Bremsstrahlung. But at lower temperature, say the atoms are neutral, they can go, they can do you can have energy jumps of your electrons. And for example, this spikes is where there are the energy jumps of the hydrogen atoms. Of the electrons are hydrogen atoms, and this one is where you have the ones of helium, okay? If you have a more complex fluid, you will have more complex cooling functions. But the whole idea is that, very generally speaking, the formation of galaxies is driven by the cooling of the gas. All right. Let's go into a bit more details, if you guys agree, in the solution of Euler equations. So again, doing cosmological galaxy simulations means working between physics and numerics, okay? So the astrophysics we need to model is described by systems of partial differential equations. So I think in the previous days or this morning, you have seen that you can describe gravity with the Poisson-Vlasov system of equations, okay? Where you can describe all your component material with a density function. And we have seen a moment ago that fluidodynamics can be described by this system of equations that we call them generally Euler equations. Okay. If you are simulating only their matter, you will only solve for the left-hand side of this panel. If you want to simulate gas interacts gravitationally between gas elements and between gas and their matter, but also with fluidodynamics. In fact, these are coupled systems of equations because effectively the gravitational potential appears as a source to the right-hand side of Euler equation. So these are coupled for the gas, at least. So now we have written them. Again, we are, based on referring to a question earlier, we are for now forgetting about magnetic fields, but we could write all of these also in terms of magnetic fields. But writing down the equation is not enough because we need to solve them. This is what we need to do, and we can only do it numerically, all right? So numerically solving this kind of equations means basically to do two fundamental things: discretize and integrate. So discretization means you can do it only, we can only solve these kind of things in general terms numerically. So it means that the fluid and matter components can be sampled, say, by n particles or n cells. You have seen this morning the n-body technique. So this gives you mass or space resolution elements. And once you have discretized your system, you have the equations that connect the system states as a function of time, but you still have to solve for the equation and integrate them in time. You might have heard of various ways to do this numerically, like the Range-Kutta method, etc. And this gives you the time steps of the simulations, or the time resolution. So now we are actually, I hope you guys touched upon the integration a little bit this morning in the context of gravity. I wanted to give you some ideas on how typically the discretization part is done in our business. So again, we need to solve a system of hyperbolic partial differential equations. There's no general solution. And there's many different approaches. And Eulerian methods are traditional schemes, but actually in cosmology, so in numerical cosmology, numerical galaxy information, there's a variety of different numerical methods, and they can be classified as a starting point in two types that I'm sure you have heard about them: Eulerian hydrodynamics and Lagrangian hydrodynamics. In the first case, the space is discretized. The problem is solved on a mesh, on a grid, and the numerical entities are volume elements, all right? In the Lagrangian schemes, the mass is discretized, the problem is solved on fluid elements, and numerical elements are, say, particles. In fact, the method we usually apply is called smooth particle hydrodynamics, or SPH. I'm gonna describe a little bit details of both. Now, SPH, the mass is discretized with particle. Still, in order to integrate the equations, we still need continuous fluid quantities to solve them, okay? So that we can differentiate them even though numerical. And so this is done with so-called kernel summation interpolant, or that's why it's SPH. So you have discretized your gas in particles. Each particle has a mass. But you want, and so this gives you, for example, the density field sampled at the position of the particles. But say we want the field at any point, so but we can only get it on a smooth fashion. And so we want the smooth interpolated version of a field. And this is an integral of the field as sampled by, say, the particles with a kernel function. If we know the field at any given set of points, the integral can be replaced with a summation as indicated here. And the key point is the kernel function. And here on the bottom is just the translation of this for the case of density. Yes, the SPH density estimate is the summation of the particle mass of m's and a window function, a kernel function defined at the position of the particle with a certain smoothing width, which is h. So the key, in fact, is this kernel function. You a priori, to do this mathematical exercise, you can use any functional form for your kernel, for your windows, as long as it's normalized to 1 and it's simple and has spherical symmetry, but it also has to have finite support. So actually Gaussians are not very good. And in the business of numerical cosmology, numerical galaxy formation, a very, very popular choice is for kernel function is the cubic spline, which is defined in every point r as a function of a certain width. This gives you, you can write it as the r over h or r over h over 2h, you can call it q, and this is the functional form of the kernel that is used in typical SPH codes. H, so the width of your kernel, is the smoothing length. And by the way, it can be chosen to be adaptive. In fact, what is typically done is that the summation, like on the left, is restricted to the number of neighbors that lie within a spherical region of radius, say 2h, 2 times the smoothing length, around a target point that you are sampling. And this is okay, is a reasonable computational cost. And typically number of neighbors are 32, 64, etc. And this is the idea behind smooth particle hydrodynamics. So now we have discretized, but we can also express the equations in Lagrangian form. So these are again the Euler equations from before, where you can write the derivatives. It's okay, there are system of partial differential equations that follow from Lagrangian. And you can do a lot of math, and you can write them down in a discretized form as on the right. These are the version of the discretized version of the dynamical equation of motions from a Euler equation. So we've gone from a complicated system of partial differential equation to a simpler one, set of ordinary differential equation. And among the various system of equation we talked about, the only one that needs to be now solved is the momentum equation, because the mass conservation and the total energy equations are automatically fulfilled by the discretization into point mass particles. In fact, I so far cheated a little bit, simplifying, because as we said since we started, we are actually solving the Euler equation coupled to gravity. And as I mentioned before, this means that you have additional terms like the gravitational potential. Or in the energy conservation equation, you actually also have a cooling function that I described earlier. So these are actually the more generalized ones that one needs to solve. And we will see later even more generalized ones. All right, I'll skip this. So as you might have heard, there are different advantages of SPH or disadvantages. The advantages are that the resolution adjusts automatically because the particle density increases where is needed. So the particles are also solved, their dynamics also solved for gravitational collapse. And so gravitational collapse brings more particles there where the density is higher. And so this is essentially is naturally adaptive. The so-called Galilean invariance is automatically fulfilled, etc. But there's no mixing. So if your gas elements are of different nature, you have to place it by hand. So suppose that your gas elements represent a mixture of hydrogen and helium. When you evolve their dynamical states, you have to tell, there's no a priori mixing, or you have to tell how much hydrogen and helium would go from one particle to another. This is called artificial mixing. Shocks are not fully captured, they're broadened, and also require some more technical stuff. Okay, SPH so far. So now let's go for the Eulerian hydrodynamics. So these are the typical traditional schemes to solve for the system of the equation of ideal hydrodynamics. And now we can rewrite yet Euler equation in another slightly different form. It's a compact form. This is it, it's the top one, okay? This is a conservation law of mass, momentum, and energy, because everything is written under the form of this big U, which is the state vector. It tells you the state of the gas at a given time. And it's all determined, the dynamics is determined by the flux vector. Okay, this is how to write it. And then of course you have your equation state. So this is a very big field. People have developed it in many ways in the past, beyond astrophysics and cosmology. There's various classes of solutions. I just want to mention them. They're called finite difference methods, finite volume methods, spectral methods, finite element methods, all to solve for these PDEs. In the cosmological Eulerian codes, most solutions are finite volume methods. They are somehow a subclass of another. And the key point is that the discretization, as we mentioned, is carried out in terms of a division of the volume, yes, into a finite number of disjoint cells. And the most practical and popular scheme is the one that you might have heard, is called Godunov's scheme. And I just want to introduce it to you, just to understand what's going on. So this is what's going on. So this is how we can describe the system. Let's do it in 1D, okay? You have your gas, all right? And your state vector U tells you about the mass, the momentum, and energy of your gas. But you discretize your volume in cells, here in 1D cells. And in every cell, you can describe the gas based on an average of your state vector. You can take the piecewise constant average, all right? This is the left-hand side here depicts the state of your system at a given time, okay? We want to say what is the system at the next time step, numerically, okay? At a subsequent time step, and so this in practice, we need to know the fluxes at the interfaces between the cells, all right? So I show it now, maybe up here on the right-hand side. So to solve for the evolution from a time step n to a time step n plus 1 means to understand and write down the fluxes of, this operator, which is the flux vector, across the boundaries of the cells. And so in practice, what you really do is you have your fluid at a given time. You reconstruct the system by doing the discretization in cells, by taking cell average quantities, and then you evolve it. You reconstruct the state forward in time, and this is indeed treating, in certain simplifications, each cell interface, the orange interface is here, as an initial value problem. Then you get your new state, you re-average your state vectors in the cells, like again here, like in this piecewise constant reconstruction, and you go forward. But of course, the tricky part is to understand the fluxes through the cells. So if you think about mass, we're really thinking about fluxes of mass from the left-hand side and the right-hand side of a cell through the left-hand side and right-hand side interfaces among cells. And so this is what is done by the so-called Riemann solvers. Well, you can. So this is just to give you some keywords, all right? And to give you some pointers to understand what people are trying to do. But yes, I don't want, and I cannot go into more details than that. And so actually I will skip some details. Okay, now, in fact, in numerical astrophysics and cosmology, we cannot use fixed grids. So in practice, why? Because in practical application, it's prohibitive to sample the entire space with the same resolution. Yeah, this requires too many cells or too much memory. And also, as we talked about earlier, our problems are characterized by huge dynamical ranges in spatial scales, density scales, time scales. And so it would be really a waste of time to solve and to do this Riemann-Godunoff scheme solution at the interfaces of all the cells at all times, regardless of, say, the density of the system. And so typically, actually, people use adaptive mesh refinement. This is what is called AMR. And I hope you can see it here. So instead of a regular grid, the adaptive mesh refinements ask for a refinement of the volume discretization upon needs. Okay, so the meshes can be regular, so like Euclidean in 3D, and so the computational volume can be divided into cubes, or it can be irregular. All right. And the refinement criteria can be based either on requiring that, say, every cell. So for example, that every cell always samples the same, more or less, amount of mass. This is a possible mass-based refinement scheme. So there are many advantages of grid codes. It can be very highly accurate. It captures the shocks and the discontinuity very well, etc. But also there are other disadvantages. It's not Galilean invariant. And a priori, you will need to do the self-gravity of the gas also on the mesh, but actually it's not required. You can also do other schemes, okay? And now we come to the convergence of these two types of solution, of numerical schemes, which are movie mesh volume methods or unstructured movie mesh methods. These are just visual representations of meshless methods, meshless separation, discretization of volumes, unstructured volumes, and as compared to the smooth particle hydrodynamics. But here, the idea that you can also make your grid move with the bulk motion, the bulk motion of your gas. These are called moving meshes. So let me say an example of these codes is the code Arepo, developed by Volker Springel. And let's go step by step. First of all, it's a code where the discretization of the volume is not in Euclidean 3D cubic cells. The space is discretized with a Voronoi tessellation. And these solutions I described earlier, the Godunov-Kiev, the Riemann solver, are applied at the interfaces among Voronoi cells, okay? But in the reference system of the mesh generating points, and these mesh generating points can actually move with a bulk motion, as maybe you can get an idea of what I'm saying on the right-hand side, where you can see a moving mesh as it's making a gaseous disk. So you can see the Voronoi tessellation, you can see the forms, you can also see tracer particles, etc. And this is the idea, for example, of more newer, but now 10 years old, but newer methods that put together the benefits of both SPH, particle-based, and a Eulerian numerical method. I want to give you more ideas about this moving mesh code Arepo. As I said, the Voronoi cells are deformable and move with the bulk motion of the gas, but also in our codes, we typically allow the mesh to be refined or redefined. So typically in our simulations with the code Arepo, we ask for the cell always to represent a similar mass of gas. And we call it the target mass. And this is a choice of the simulator. And this gives you the resolution, say, of a simulation. So for example, here you see the same quadrant of a halo, a better and better resolution going from left to right. On the top is the Voronoi tessellation. On the bottom is the density field, okay. But what I want you to see, so what we keep fixed in at this level is the target mass, is the mass that the Voronoi cells are meant to contain. And in the next levels, we make this target mass smaller. And then you can see the cells are smaller, but they also are smaller and smaller there where the density is higher and higher. And just to give you an idea that we mentioned earlier, Kelvin-Helmholtz instabilities and moving mesh codes do better jobs than fixed grids. And at capturing, for example, these are the type of various type of instabilities. And my colleagues in the past have also shown, and many other people in the past have also shown how different case tests result with standard SPH or improved SPH method versus moving mesh methods. Before taking the break, if you guys agree, I just wanted to give you an overview of the available cosmological codes that adopt this kind of numerical method. So first of all, just let me be very clear. We are talking about cosmological codes. So these are codes where everything I've said until now takes into account the fact that the universe expands. How is this done? I think you've seen it this morning, I hope. But the idea is that the expansion of the universe is accounted for the fact that everything is solved in comoving units, in comoving coordinates. And then the expansion of the universe, given a certain cosmological model, is given by how you do the mapping between comoving and physical units or proper units, and how essentially a redshift translates into actual giga-years after the Big Bang in the simulation. So I will only mention mostly cosmological codes where this is accounted for. Also, for codes for galaxy simulations to be practical in the cosmological context, the solutions of the equation has to be done in ways that the time integration is not the same across the domain volume, the volume domain, simulation domain. And this is because, say, you are solving for the gravity equation, no? or you're solving for a Euler equation in your discretized manner. But you don't want to do the numerical calculations as many times, say, in a void as in the center of a cluster. Because in a void, the density is very low and things change very slowly. While at the center of a cluster of a galaxy, things change much faster. So you have to actually solve to get accuracy, to get good accuracy, your equations much more frequently. And so then current cosmological galaxy formation codes must be with individual time steps, okay? And not global time steps. This is key, and this makes the coding quite hard. And finally, to make successful at the current time galaxy formation simulations, the code must be parallel. This code must be written so that multiple computers can work at the same time, and so they oftentimes, like in Arepo, so far we have used it in a distributed manner parallel through, for example, MPI. All right, so these are examples of code on the top that satisfied what I said. Grid codes, moving mesh codes, and SPH codes. Like adaptive mesh refinement grid codes and cosmological context are Enzo or Ramses. The moving mesh codes are Arepo or Gizmo. SPH are Gadget or Gasoline, etc. Arepo, Gadget, Enzo, Gizmo, they're all public. So if you want to use them, you can go download them and play with them. Okay, in fact, I've only described the gravity, hydrodynamics, and cooling part. But even with these three physical processes, we still don't do galaxies and stars. But we do this after the break. But what I wanted you just to be very practical. So when we run galaxy formation simulations with Arepo, the resolution elements are their matter, stars, black holes, which are particles. They all interact gravitationally. And the gas are cells, and they interact both gravitationally and hydrodynamically. Okay? And this is another example of how the Arepo code functions. But to be even more practical, I want to show you what is the typical output of a galaxy formation simulation. Okay? This is the snapshot. This is what we decided to save at a given point in time as the simulation was running. So if you were to do only a dark matter simulation, you would need to know the coordinates, the velocities. So these are 3D double, 2 times 3D doubles, and say the potential sample by the dark matter particles. But if you were to do only a dark matter, only gravitational simulation, but if you do a hydro simulation, you also get the gas cells. And so, for example, we decided that we need to save for future usage the coordinates of the cells, the density of the cells, the mass in the cells, the potential probed by the cells, or in our case, these are magneto-hydrodynamic simulations, so the magnetic field strength in the cells is a 3D vector, the internal energies and other things. And if you solve for also star formation and supermassive black hole physics, you also have many, many other variables that you need to solve and possible data sets that you may want to save for future usage. So this brings me to numerical resolution and the physical ingredients, additional ones of galaxy formation. But I don't know whether it's standard. Did you guys take breaks in previous classes, or shall we not? I'm referring here to our, what do you guys want to do? Do you prefer to keep going? Raise your hand if you prefer to keep going, or instead of a 5 minutes break.
I guess there is half an hour left, right?
Yes. Shall I just keep going?
If I don't explain, yeah.
Yes, sounds good then. Okay then. So in the meantime, I also paste here the a link, okay, to a file. Okay. Where you can place some questions in case there's no time today and I may get to them later in the next days or so. So then you should be able to go there and I just set up something and let me know if you can write it down. Okay, good. So I keep going. And someone of you asked me, what are the limits where the simulations can go to? And this is very much answered by the concept of numerical resolution. I'm sorry. Can you guys see again my slides? Raise your hands or speak up. Or yes, or a chat. Perfect. Thank you. Okay. So actually, for those of you who are not of the business, numerical resolution can be very confusing. And this is normal because it is actually very complex to quantify the numerical resolution of hydrodynamical schemes. All right. So there are two types of resolution. Well, there are three types of resolution: mass, spatial, time resolution. In terms of time resolution, this is never a problem, so nobody ever talks about it, so it's fine. But mass resolution, spatial resolution may become important to know. So the mass resolution is essentially tell you the mass of the gas elements, whether a particle or a cell. In the case of SPH codes, is the mass of the gas particles that you have decided for the discretization of your total amount of gas. And for grid codes is the target mass of the cell in case this is kept fixed. The spatial resolution is the spatial accuracy over which the Euler equations are numerically solved. And so for the SPH, this is essentially given by the SPH kernel smoothing length, often given in terms of these neighbor numbers. In the grid codes is effectively, okay, the size of the cells in which you have discretized your volume. Okay, so this is usually called smoothing resolution, smoothing length for the hydro, as opposed to the softening length, which is the resolution, the spatial resolution of the solution of gravity. Clear? And say the mass of the gas particles when you do SPH, or the number of cells, initial cells in which you discretize your volume at the beginning of your simulations, these are choices of the simulators and determine the accuracy and quality of the simulation. So more particles, smaller mass, better resolution, okay? More cells, smaller volumes, better resolution, okay? And so this is why we typically describe them like that. I will leave in the slides much more inputs about the numerical resolution, but I think because I sense that you might have not heard too much before about these topics, it would be a bit too much to go into that directions. Instead, I want to go to the difficult parts, the really difficult parts about modeling galaxies in the cosmological context, which is the modeling of the physics of galaxies. So we go back to this slide of the setup of the ingredients, matter components, physical processes, the domain you want to simulate. And we focus on the physical processes. We've talked about gravity, we've talked about fluidodynamics. We have also talked about cooling and the fact that atomic processes like radiative cooling of the gas must be included in your equations. But there's a number of other physical processes that might be relevant depending on the problem you are doing. At the minimum, if you want to understand the evolution of galaxies, you want to do star formation. You want to include stellar evolution, the production of metals. For us, these are elements beyond the hydrogen and helium. You must include feedback from supernova, from supermassive black holes. if you're very interested exactly on the radiation fields, and there are, for example, domains where this is important, you actually need to follow the evolution of photons, and you do radiation hydrodynamics. If you need or want to follow the evolution of magnetic fields, you do magnetohydrodynamics, etc. So many of these processes, oopsie, sorry, I went too far. Many of these processes are essential for astrophysics of galaxies. But as you can imagine, no, the atomic processes of course, but even the formation of stars, the explosion of supernova, they all are unresolved in the kind of simulations that we can do nowadays. They occur below the physical resolution of the simulation. So say if you are doing a grid simulation, below the grid cell sizes. So in other terms, the Euler equation written in compact form has a source terms, again, not just gravity, but other source terms and cooling, that encapsulate all messy astrophysics that adds complex and typically actually poorly understood phenomena and source terms. And so we include them by writing down equations which are coupled, as you can see here, to Euler and gravity equation by using laws that are suggested by observation or by theoretical models which are tailored to just address one particular physical problem. Or in other cases, we actually implement them via lookup tables. People tell us what are the atomic processes and the cooling. We know the cooling functions. If I know the density of the gas and the temperature of the gas and the composition of the gas, I don't need to calculate all of this all the time by going back to atomic physics. We can just tabulate them and give them to the code through so-called lookup tables. So let's go into a bit of details of star formation, stellar evolution, stellar feedback, and supermassive black hole feedback. So you get a sense of what's happening in these codes. So star formation. So we know stars form at the center of galaxies. It will always be subgrid. So for example, this is a simulation of a galaxy. You see the Voronoi tessellation, seeing the galaxy edge on. So you have a thin disk. And in large volume cosmological galaxy simulations of today, the average gas resolution elements is something that goes between 50 parsec, at best 10 parsec, up to kiloparsec or more. So these are larger spatial scales than where the sizes of star-forming regions, of giant molecular clouds, of much more than so, the supernova explosions. Okay, so in this numerical model, star formation means conversion of gas elements into stellar particles. So a fraction of the gas elements, whether gas particles or gas cells, can be transformed into other type of resolution elements that they get a new label, and then they they are required to solve different sets of the equations in the code, which we call stellar particles. Okay, typically. So, and the basic idea is to convert only gas that is dense into stars. But different models assume different values for the density threshold. So in some cases, it's really a density threshold. It's really like this. We go to every gas cells, say in our simulation, we ask, what is your density? Is it larger or lower than the density threshold that we have decided being the density threshold for star formation? If yes, produce a stellar particle. Actually, this is done much more complexly. So it's done stochastically so that observationally empirical laws are satisfied. So we know, for example, from observation, the star formation happens on certain time scales, and this spawning of stellar particles happens stochastically so that the time scales are consistent with empirical knowledge. But also, when a new stellar particle is formed, it actually represents a population of stars that are all born at the same time. And they are born at the same time, but actually inside it, we can sample stars of different masses, not just sun-like masses, but 0.1 solar masses, or even 10 solar masses, or 100 solar masses. At the beginning, when a stellar particle is formed, we need to decide the initial stellar mass function. And in this plot here, I just show you some possible initial mass functions. Is this clear? Star formation in this code is conversion of gas elements, particles or cells, into stellar particles. And people do them differently. I skip on this, but I leave it in the slides for your reference. So the stellar particles give a beautiful example of what does subgrid modeling means, okay? Because a real star is on average a solar mass, but a stellar particle may be something like 10 to the 3, 10 to the 4, 10 to the 7 solar masses, or even larger for worse resolved simulations. And as I said before, each represents an entire stellar population with a certain initial mass function at formation, so how many stars of a given mass there are in each stellar particle. And also the stellar particles can evolve. The stars inside the stellar particle of different masses evolve along distinct tract, and this is taken care into the code. It is modeled in the code. At each time step, the stars, the ensemble of stars can evolve, can age, can become older. And by doing so, they can synthesize heavy elements like carbon, oxygen, iron, and they can lose mass in the surroundings because of stellar winds. Okay, this is what we mean by stellar evolution. But some of the stars inside the stellar particles can also reach end of life. They can go off as core collapse supernova, and they can release, say, something like 10 to the 51 ergs of energy. So in the codes, this mass momentum energy output from the stellar particle is coupled back to the gas, is donated back to the gas. And this is the feedback. So let me go give you some, oopsie, I wanted to go here. So the IMF, the initial stellar mass function, is a choice. There's no knowledge, I mean, no fixed knowledge. We have an idea what shapes it could have, but it's still unknown. This is what, as I said, we call stellar evolution or metal enrichment. And so in practice, we implement this by asking the yields of a given star, of a given age, of a given metallicity, meaning how much of a given elements does this star produce? And as I mentioned earlier, we use lookup tables for this, which are based on observation or a mixture of observation and small-scale simulations. And the return and couple back of mass, momentum, and energy is the feedback. But how exactly this coupling is done is dependent on the code, and this is at the forefront of our modeling, is what we are trying to do better and better. So stellar feedback then. Let's talk about feedback, and let's talk about feedback from stars. So the basic idea is to reduce the amount of star-forming gas. So let me tell you why. So I show you at the beginning that the motion of gas from star-forming region of galaxies are observed. We observe them. And powerful energy injections are known to be triggered by, say, supernova explosions, okay? This is the basic fact. So we want to mimic this observational fact. But there is another practical problem. This feedback is needed to reproduce the amount of stellar mass of observed galaxies. So if you take a cosmological simulation of dark matter and gas and add recipes for star formation and cooling, well, if you do only that, as it was done 15, 20 years ago, all the gas will be converted quickly into stars and produce too much stellar mass. This is what is called the overcooling problem. And another way to show it is by showing a galaxy's stellar mass function. So the number of galaxies of a given mass in bins of stellar mass. This is the shape of the galaxy stellar mass function observed. These are Milky Way-like galaxies. These are very massive galaxies and very rare. These are small galaxies and very frequent compared to the massive ones. This is a rescaled version of the dark matter halo mass function that comes from embodied simulations, for example, or analytical projector. And this is what would happen if you were to put, scale the predicted dramatic halo mass function for the baryonic cosmological fraction. So they're not the same shape. Something makes the dramatic halo mass function multiplied by the baryonic fraction to bend into the observed galaxy mass function. And these are this feedback. All right, I'm going to skip the next. And the stellar feedback are really implemented in a number of manners. And for example, I just want to give you the example of this, of the simulations I've been working on. The implementation of stellar feedback is very, very crude. We literally transform parts of gas cells into wind particles, so that a new type of particle that then for a moment, for a while, does not interact hydrodynamically, but only gravitationally. And we give it a kick, we give it a velocity in a given direction, so that then we remove gas from the star-forming region of galaxy and bring it to lower regions of galaxies, lower density regions, and solve the problem of too much star formation because of too much conversions of gas into stars. The next few minutes are for another form of feedback, supermassive black hole feedback. We want to mimic what is observed. And active galactic nuclei and supermassive black holes are now ubiquitous. Everybody observes, there's millions observed AGNs. But we also know from more detailed observations that powerful energy injections are known to be launched from the sides of supermassive black holes. So we want to mimic these observations, or try at least. We also know, based on numerical experiments 15 years ago, and more recently, that we know a certain very energetic feedback, more energetic than with the stars, with the supernova, to actually stop star formation in very massive galaxies. So for those of you who are not astronomers, very massive galaxies are actually not forming stars at a very high pace today in the real universe. And it's a big question on how did they quench, how did they stop forming stars? And in our field, the solution is given by supermassive black hole feedback. So now, there are a number of difficulties now. Firstly, nobody knows how these supermassive black holes form, literally. It's an open question and big sector of research in astrophysics. And so in our model, we usually place them by hand as so-called sink particles. So these are particles, they interact gravitationally, like the collisionless dark matter, the collisionless stars, but they can also change mass. So in fact, supermassive black hole particles can grow in mass either by accreting gas from the surrounding where they are, or by merging with other supermassive black holes. So now, again, in the reality, the accretion disk of a supermassive black hole is tiny. It's way, 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 way smaller than the best resolution cell in any cosmological simulation or even normal simulation. So we actually had to tell the code by hand what kind of accretion rates of gas into the supermassive black holes should be done. And this is, again, we resort to theoretical understanding, like we implement usually, so for example, an accretion rate of following a so-called Bondi formula. We don't allow the supermassive black holes to accrete faster than the so-called Eddington ratios, Eddington limits. But then we also have to decide the initial mass of the supermassive black holes and in which halos or galaxies these supermassive black holes are seeded. And then, as I said, the accretion and the position. And this is all about making supermassive black holes. The big question, and different simulations, they do different. And the big question is how supermassive black holes exert feedback on the surrounding gas. So this is the problem of supermassive black hole feedback. And there are many possible subgrid implementations. The idea is to, again, return mass, energy, possibly momentum from the supermassive black holes to the surrounding gas. But then, as I said, we are talking about a very discretized situation. So this is, for example, a halo with the Voronoi tessellation that represent the gas cells, and we have a supermassive black hole at the center. So there are many schemes practically that people have used in the last few years on how to numerically, practically implement subgrid supermassive black hole feedback. In some models, you simply dump some energy from the supermassive black holes into the surrounding gas isotropically under the form of thermal energy or internal energy. In other cases, you dump thermal energy not around the black hole, but in far away through the halo to mimic the endpoints, the ones we have seen at the beginning, the endpoints of these collimated jets. Okay. You may do it once in a while, very energetic dumps, or you can do it more frequently with smaller dumps of energy. You can also decide to actually donate momentum, so really to give a kick and change the kinetic energy of the gas in the surrounding of the black holes. And these produce so-called black hole-driven winds that, again, are meant to mimic maybe the jets, the collimated jets that we saw before, or not. So in some cases, you can do it in one direction, in isotropically, or as a form of jets. Or you just say, I really don't know, you're totally agnostic, but the only thing I need to do to stop star formation at the center of massive galaxies is by reducing the cooling of the gas that could be transformed into stars. How do you do it? You heat the gas. And you heat the gas reservoir all around the supermassive black hole or around the galaxy. So as I was saying all this, you can imagine there's many choices, not just of what to do among these possible scenarios, but also of how to implement them. And different simulation codes and different simulation projects adopt different things that have been chosen by the developers, given the goals of their models. And let's keep on that. And so, as you might have understood, differently than gravity-only simulation, galaxy simulations are affected in a way by a large and uncertain parameter space. So the functional forms and the inclusion of physical processes are by choice. They are dictated by the scientific applications and by the computing capabilities and the capability of writing the code. And once you choose the processes, you still have a number of choices to make on how to practically implement them into the code. So these are parameter values. Like the table here lists the parameter values of two very successful and very recent cosmological galaxy simulations, Illustris and Illustris TNG. So these parameter values are chosen from a mix of ab initio results or smaller scale simulations in theory, observations, and we typically use them in the so-called development phase. So we explore how our model return different galaxy properties by changing the choices of the parameter values. Of course, you have to choose which properties to look at, and you need to choose what parameters even to explore. So this can be anything from a parameter space from 10 to 50 dimensions or so. And there's various practical ways in which people have done this calibration and tuning step. And the idea is to pick up 1, 2, 3 observational constraints on the galaxy properties that to fix the model, and then to run with this best model that you have found the best possible simulation you can. So these are, for example, just to give you a sense of how things could be different, is like is a 10 megaparsec volume. On the top is the results of the so-called Illustris model, and then the bottom of the so-called next generation Illustris model. And the great difference between the two is the implementation of supermassive black hole feedback. On the left is gas density, then gas temperature, gas metallicity, and stellar mass. And what I want you to notice is, for example, how different are the density fields of the cosmic structures and the temperature of the gas, or how the heavy elements are spread in the large scales at low densities. In fact, the illustrious model is already ruled out, which is why we went to the TNG model. And we knew that we had to change the feedback from supermassive black holes to make it more compatible with observations. So we are closing with some example of state-of-the-art simulations. So I bring them back from our previous slides. Mostly I want you to focus on large volume simulations, the one that give you statistics, illustrious, illustrious TNG, Eagle, magneticum, horizon AGN, oopsie, etc. Or possibly zoom in simulations. If you're interested, I can point you to what that means. So these are new, so these are from 2014, 2015. In fact, in 2014 and 2015, illustrious and Eagle were really the first simulation that show on a representative volume of the universe, about 100 megaparsec, that with one unique set of ingredients, gravity, hydro, cooling, galaxy formation model, we could actually make thousands of galaxies that span the diversity in morphology, which is observed. So this is, they really set a new era for this kind of simulations. I skip here. And I would think that really the forefront today of this kind of simulation is represented by a model that I've been working on. It's called TNG 50. And this is a 50 megaparsec volume where we actually reach resolution that was unthinkable just a few years ago. So like our stellar particles and gas elements are below 10 to the 5 solar masses. And you say, oh my God, it sucks. Well, yes, but compared to the fact that, you know, stars are on solar masses, but it's really very good. And it also means that we can solve galaxy formation processes on about 100 parsec resolution in the star-forming region of galaxies. But it was expensive, yes? So it ran for more than 1 year, 24/7 on 16,000 computing cores. So TNG 50 is one of the flagship runs of the so-called illustrious TNG simulation, which I want to advertise because it's the one I've been working on, which is made of 3 main simulation runs. We call them TNG 50, TNG 100, TNG 300, because the name tells you the extent in cubic megaparsec of the cubic volumes that are resolved. And these are cosmological, magneto-hydrodynamical simulations for galaxy formations. While we go to the end, and just to take a break, I just wanted to show you one movie of only one galaxy of the thousands in the illustrious TNG simulations. As it evolves from high redshift to today, in the center panel is the gas density. The 2 insets on the right hand gives you the stellar light, and again, the gas density on a zoomed in region in the center. And the left-hand side bottom panel shows you the matter, first the matter, and then we go into gas density of the large-scale structure around this galaxy. So this galaxy is one of many, many thousands in these 50, 100, 300 cubic megaparsec volumes in which are simulated in illustrious TNG. And you can see now that this particular galaxy at this point is a very nice disky galaxy with spiral arms. We can go around them and show other fields of the gas, like the heavy elements on the left. And this galaxy, for example, really encodes the cosmological context. This smaller satellite is about to merge with this galaxy, and it actually perturbs the galaxy, making the disk change a little bit its inclination and rotation. So these simulations are incredible resources. They are open-ended laboratory for a number of studies, including about dark matter and gamma rays. And if you guys are interested, actually, their output is completely fully public. And we have put also out many Python, IDL, MATLAB scripts or other ways to do basic I/O. And so to get the data and to manipulate the data. So if you're interested, please take a look at our website. Now, after this lecture, you should have an idea of what these simulations are all about, and should have got a better idea of the glossary. So illustrious TNG is an example of cosmological gravity plus hydrodynamics. In fact, magnetohydrodynamics simulation for galaxy formation in a uniform volume using a moving mesh code over a periodic boundary condition. And now you know that cosmological as opposed to isolated, gravity and hydro as opposed to dark matter only, magnetohydrodynamics as opposed to simulation that don't care about magnetic fields, including galaxy formations, including cooling, including feedback from stars, star formation, stellar evolution, etc. Uniform volume, meaning these cubic boxes, and so not zoom, and moving mesh, it's the mix of smooth particle hydrodynamics and Cartesian grid numerical techniques. And so this is a way maybe to conclude. I will leave maybe in the slides, if you guys agree, some selected results that you guys may be interested in browsing that are predictions from this type of simulations. Yeah, so what do you guys think? Unless you want to see the results together with me, and then we can take another 5 minutes.
Yeah, so in any case, so you started like 5 minutes later, so we still have like 5 more minutes.
Yeah, shall we do that? So I think I want to, thanks, then it's good. I think I want to bring home a little bit more practically why these simulations may be of relevance to you guys. So do you guys, I hope you see again the slides, and if you do not, please shout.
Yes.
Okay, so I've described gravity, hydrodynamics, star formation, stellar feedback, supermassive black hole feedback. These are all baryonic processes. And these simulations are incredibly rich and also incredibly powerful, because they also tell us about the possible back reaction of baryonic physics processes into the phase-space properties of dark matter. In the particular case of the ones I talked to you about, we are really focusing on cold dark matter, so a particular scenario, right, for dark matter. But since I say 10 years, people have realized that as soon as you put gas and as soon as you put galaxy physics, predictions for the phase-space properties of dark matter are different than the ones you obtain from n-body or gravity-only calculations. And here I give you an example based on a simulation of a Milky Way-like galaxy, where we could compare the same galaxy simulated only with gravity and only dark matter versus gravity and hydro and stellar physics and star formation. The differences are important, and they are across the typical diagnostics that we study dark matter for. So we know dark matter profiles. Halos are described by dark matter profiles, which are typically in n-body only simulation, Navarro-Franken, well described by Navarro-Franken-White profiles. But this indeed is, as they say, is the 3D spherical average density profile of core dark matter in this galaxy with only gravity, so dark matter, and the corresponding total density profile will be the solid, but even the one that is only dark matter profile in the full physics hydro galaxy run Aries is in that. It's different, it's contracted, it may be cored. Baryonic physics changes the shapes, the 3D shapes of dark matter halos. We know them, dark matter halos are not spherical. They're triaxial, typically. In fact, baryonic physics makes them a little bit more oblate in the regions where there's also gas and stars. You know, the very popular missing satellite problems now is totally surpassed, I would say, as of these years. But it's also very important to realize that the abundance of subhalos depends on whether you are, you know, the abundance of subhalos depends on whether you are solving for gravity and dark matter only, or for full physics simulations. And also something of relevance that you might have touched upon is that is relevant for the detections for dark matter is, for example, what is the expected velocity distribution of the dark matter fluid as the Earth goes around the sun and in the galaxy. And this velocity distribution of the dark matter is very different if you do a dark matter only simulation or a full physics galaxy simulation. This is the case for Milky Way-like galaxies, but these kind of issues are emerging across the mass scales. So baryonic physics affects the distribution of dark matter within halos actually across quite some mass ranges. And another way to show it is by showing the concentration mass relations, for those of you who are familiar with it. The concentration mass relation from n-body only simulations, depending on cosmology, is a power law like this in these plots. Like dark matter only are the dotted curves. The same relationship between the concentration of dark matter halo and the total halo mass changed to something else in different models, meaning in models where we also include baryonic physics. So this is, again, it's important if you guys are interested in predicting the expected signals of the presence of dark matter at the center of halos. And finally, zooming out a little bit, baryonic physics generally, so baryonic physics that occurs in the center of the galaxy can also affect the clustering of matter, not just the total matter, but also the dark one, and also on scales which are much larger than the scales of halos. So I don't know if you guys are familiar, the clustering of matter can be described with the power spectrum or the two-point correlation function, for example. And in these plots, you see the ratio between the results of the power spectrum obtained from a full physics galaxy formation simulation and the dark matter only counterpart. Okay, I want you to maybe look at the one which also, it's only about dark matter, is it dark matter power spectrum. And it's this ratio. So it's the power spectrum only of dark matter, but in simulations that include full physics and also gas versus not. And as you can see, these are spatial scales on the bottom, the x-axis. The deviations from dark matter only predictions can be quite large, and can be quite large on scales that are much larger than the typical scales of halos or galaxies. And at the moment, different models produce quite different predictions, but we have actually pinned down the reasons for them. But the point is that whatever model you pick, it seems that they are actually predicting a clustering of matter that is different from n-body-only predictions to much more than the 1% accuracy that is declared these days to constrain dark energy and to do precision cosmology. And so, yes, this makes my conclusions. I mean, I just wanted to give you more practical examples of what can be done with this kind of simulations. And I close with a movie. This shows you the velocity fields of the gas, and it's really the quintessential demonstration of a galaxy formation simulations, because here on the bottom you see, for example, gas motions driven by the supermassive black hole feedback in our simulations. This is TNG50, and soon you will see again gas motions due to supermassive black hole feedback coming up on the right hand side. In the meantime, you see galaxy merging with others and big collapse structured forms. You see here, this is another supermassive black hole feedback and collapse objects moving around, being stripped as they move in their potential due to dark matter, gas, stars, supermassive black holes. And now the movie goes to show you not gas field, but stellar mass. This is the typical assembly across billions of years of evolution of a very massive galaxy cluster. With all the satellites and the brightest cluster galaxies like these two galaxies that are gigantic, like 10 to the 12th solar masses, they are now merging to make an even bigger galaxy. And this concludes what I wanted to show you.
Thank you, Annalisa, for the spectacular lecture. So is there any questions?
So can I have a question for you guys? Maybe because I didn't know. So among those of you who are live here, can you raise your hand if you consider yourself a physicist rather than an astronomer / astrophysicist? And so the others, I don't know. Okay, not many, but I give some more time. Because I don't know whether you guys are just yeah, okay, all right. And so the others are doing more astronomy, astrophysics, or astroparticles, perhaps. Yeah, okay.
Yeah, Annalisa, the thing is, I think we have more people from particle physics in the audience than from astrophysics, you know, so.
Yes, I got it, Miguel, thanks. Okay, yes. So, but cool. No, it was just to get an idea. Astrophysics, perfect, yes. Yeah, there's a question, I think, or it was still a recent. No, okay.
There is also opportunity to ask questions on Gather Town later.
Oh, yes, but guys, I have another talk, so I will not be there.